Okay, hello, my name is Petr. I'm author of the paper When LLM is apprehensive about its answers and when its answers is justified. I'm studying at second year Master Science in Skoltech. So this is our paper from our lab, Lars lab. About our problem, which we was trying to solve. Modern large language models have especially in scientific deep domains. So when you are trying to ask a very hard question, you can see example below here. This is biology, multiple choice. Large language models have problems with really specific knowledge. So we was trying to estimate this correlation between reasoning in solution of problem and knowledge. So when we are showing this correlation, we can help to adapt reasoning-based models to vary their answers depending on complexity of questions. So also when we have overconfidence in incorrect answers, this can have really harmful consequences, especially in large models with 100 and more billion parameters when you are believes in this. So next, about our key contributions. We used MLU Pro dataset. This is classical MLU, but more clean, without bad question answers, which was leaked before. So this is data set with multiple choice from 3 to 10 variants of answer, and we use token-wise entropy on this one token, and we also use model as judge approach and MTBench as an evaluator. It is also model as judge, but evaluator of another model as judge. So our key findings is about very poor performance of model as judge approach and about MLU Pro biases, because of we have really different reasoning requirement in another topics, because in MLU Pro we have 14 different domains like biology, math, computer science, etc. And any of these have different reasoning requirements. I'll show it later. So let's try it. We can see that, for example, engineering is 90% need reasoning and philosophy is 50% need reasoning. So we can see bias. About our experimental setup, as I said, 12,000 STEM question answers. Our models, we use all family of Qwen models. I mean, not all, but about 6 models from 1.5 billion parameters to 72 billion parameters, Microsoft model FE4, and French model Mistral small, 24 billion parameters. In our model as judge approach, we use Mistral by IP. This is more than 100 parameters, so we believe it. About MTBench, this is example of our prompt, how we are trying to estimate complexity. So we are just, we have 5 quantiles with, and we are trying to estimate hardness of question. For example, undergraduate easy or postgraduate. This is name of hardness for our question. So about our pipeline, which we provide, let's start from the start. We have question answer. Next, we are going to evaluate it by Mistral as model judge. We are scoring this, and we use categorical entropy. Categorical entropy. This is like prompt. This is how to say. We are trying to estimate entropy. We are model judge. So we are literally trying to say it. Do entropy estimation of these question and answers, and we are use token-wise entropy, our core idea. So also we check all of this with MTBench. If we have less than 8 by MTBench, so MTBench is we are scoring every question answers like from 1 to 10. So if we have less than 8, That means that our question scoring is incorrect and we are trying to rescore it. Next, after this, we are going to estimate ROC AUC of this. We have entropy scores. We are token-wise entropy. And we are model ZASH categorical entropy. And we have reasoning requirement feature. We have knowledge requirement feature and reasoning steps amount. This is the same things. So because knowledge is like inverse reasoning, we have such results that reasoning is the inverse knowledge, and reasoning steps amount is just not just binary reasoning, but like how many steps do you want, like mid, low, and high. So, we subsample by these features and by subject domains, for example, biology and the reasoning requirement. This is a subsample, and trying to estimate ROC AUC scores by correctness label, because we know. So yes, we are asking our models to answer, and then we estimate by correctness label because we know correct answers. So about results, as you can see, I'll explain. When we have ROC AUC about 0.5, this is like random. So we are trying to target ROC AUC more than at least 0.65, and as we can see, we have so we can see dependence on model size. So models with big parameters, for example, Qwen is perform better than, for example, Phi4 from Microsoft or Mistral. So that was obvious, and also we can see that a model judge approach fails because we cannot see any correlations with errors, and AUC on model judge approach is about 0.5. And on knowledge-heavy domains like biology, I mean knowledge-heavy or low reasoning, this is the same. We can see better ROC AUC. So when we need a lot of reasoning, this means that model will overestimate their confidence, and another. So next, about reasoning versus knowledge. So yes, we can see that this is also ROC AUC. Sorry for bad picture, but we can see that when we have reasoning high, we see lower ROC AUC on every model, and when we have reasoning low, we have higher ROC AUC. So we can say that this data set NLU Pro, of course, has bias by reasoning, and but low reasoning still provides better ROC AUC. Let's see now on entropy distribution. So what is it? We have entropy, and we have amount of question answers, and this is all Qwen families. And on this picture, when we have blue, this means that we answer in. So you see, yes, when we have blue, it means that we have correct answer with such entropy. So in our situation, when we have low entropy, so this means we have very high confidence, we have to answer correct as much as it possible. And from another side, when we have 2 or 1 or I will say 1 or more entropy, we want to have a lot of incorrect answers. Let's go next and look at our metric for this situation. This metric is called expectation calibration error. You can see formula below. And we will split our entropy distribution by quantiles. And we can see accuracy plot with confidence. And we have very strange result because little Qwen, the littlest Qwen, has the best results, the best, you can see 0.242 in calibration issues, the best when we have, as I said before, 0 accuracy. When we have 0 accuracy, we have when we have 0 confidence, we have 0 accuracy. And from another way, when we have or confidence 1, we will have 1 accuracy. And in this picture, we can see that Qwen 1.5 billion parameters is the best calibration, and also main point is that this is monotonically progresses, and this is interesting. So to the next slide, about our conclusions. Of course, the main conclusion that model judge approach needs improvement in this deep domain scientific question answering task. Also, we need more balanced data set to improve our pipeline because of reasoning bias. As we can see before, when you have more parameters, this is better. And entropy fails for questions that requires high amount of reasoning. That's obvious also. So about discussion, yes, you can see our GitHub, our archive paper. About discussions, what should we provide next? We can provide more, as I said, more balanced scientific question answering data set. We can do in the future fine tuning with Mistral or Llama on low confidence data set subsample. The idea about this is to fine tune our fine-tuned model, for example, Llama 3.8, on little subsample with a low confidence rate from our pipeline. So we will improve compute with this because we will fine-tune on more little part of data, and also we can. So I guess that's it about discussion and acknowledgements. Thank you for my team, and thank you. Maybe questions?
Thank you, Petr. Do we have questions from the audience? Yeah, please.
Thank you for your speech. And I have some question. As we know, if we use some regressive generative models, then we can see hallucinations. And uncertainty modeling can help us to detect this hallucination. But what is hallucination? Hallucination is semantic mismatching between answer and input context. And do you compare, as I understand, we have two ways to estimate this mismatching. Inner way, which is based on cross-entropy, on some epistemic uncertainty modeling, and outer way, which is based on mismatching estimating with additional model, for example, some cross-encoder or using with some semantic metrics such as like as Bayes score, etc. And do you compare your approach to estimate uncertainty with some outer approach which can be based on Bayes score between answer and context, or this approach can be based on self-checked GPT or special cross-encoder to semantic mismatching detection?
Okay, thank you for question. In this task, we have one problem. We have multiple choice. So when we are asking a large language model to answer, it just provides to our only one token, just A, B, C, or D. Yes, this is multiple choice MMLU. So when we are talking about open answers, we are trying to, in the future, we will try to use reasoning and to provide different methods on entropy or uncertainty estimation based on this reasoning corpus. So reasoning has a lot of words, and we can do a lot of interesting things and find a lot of interesting results. But here, this is impossible because this is not open.
Semival evaluations. As I know, 2 years previous year, next current year, there was a special track devoted to hallucination detection on Semival. And this is a very interesting track. There are many artifacts, such as papers, open code, for analysis of uncertainty in large language models and other features to detect hallucination. Do you analyze this data from some of our workshops?
Yes, we analyze data, but not from Samuel workshop. Maybe yes, but I don't know what is Samuel workshop.
This is well-known series of workshops, but in previous year and this year there was a special track, hallucination mushroom track devoted to hallucination detection in large language models.
We didn't try this, but I can tell you about another data sets which we were trying. And so we was trying to use ARC. ARC, this is a huge data set, about 6,000. It has two parts, challenging and easy. And this is questions only about artificial intelligence. Yes, we are trying to use all of these experiments on it, but we have problem because there is no how to say big difference on topics. So here we can see biology, philosophy, law, economics, computer science, and on ARC we have only computer science, and we find out a lot of biases with reasoning too, but our paper is not about it. And also we find a cool data set, GPQA, Diamond, all modern large language models benchmark on this data set. You can read any paper, a modern, for example, Qwen or Anthropic, I mean from February of this year. And you will see GPQA, but problem of GPQA is that very low data set. It has good PhD or postgrad or even doctor questions about scientific, but 400 with 50 amount. So we was trying to find trade-off between amount and between difficulty, and our choice was MMLU Pro. Yes.
Okay, thank you. I have another small question. Do you analyze relation between uncertainty and quantization of large language models? For example, if we use some Qwen with 7 billion parameters, and we use this version but quantized in 4 bits or in 8 bits, and what difference between behavior original and quantized model on the same work knowledge data set, and what difference between uncertainty model, original and quantized model?
Thank you for the question. No, we didn't measure a quantized or unquantized model. We just take classic Qwen, but I think that's a good idea for research in the future. Our models are not quantized, no GPTQ, so just classical large language models. I mean, from our experiments.